Welcome to the last installment of this video series on my doctoral research. In the previous two videos, we have covered the introduction to this research problem, relevant mathematical background, and the development and formulation of a physics-informed deep learning paradigm for traffic state estimation. In this video, we're going to focus on analyzing the PIDL performance and discuss the strategies to improve the estimation results. We are going to, in this section, we are going to showcase the limitations of PIDL with the hyperbolic version of LWRPD equation and the contrast of these results with the parabolic version of the PD. We are also going to see the implementation of PIDL with nonlocal physics and how that's also going to improve the TSE results. And finally, we are going to conclude this research work with suggestions on future research directions. So here's the overview of the first case study, in which we use a synthetic ring road testbed data for the comparison or to showcase the contrast between the PIDL performances. So in the figure on the right, on the top, we will see this ring road testbed data, which is configured with the hyperbolic version of LWRPDE. This LWRPDE does not have the diffusion term and cannot secure a strong solution. So in this case, we can only find a weak solution for this PDE. And in the bottom, this is a data set that's configured with the parabolic version of the LWR equation. Because of the addition of the diffusion term, this PDE will have a strong solution. And the relevant information about what is strong and weak solutions, or information about the hyperbolic LWRPD, you can refer to the first video where we covered the mathematical background, and also the second video where we formulate the PIDL paradigm with LWRPD here. So on this slide, I just want to emphasize on these two data sets are almost exactly the same. The difference measured by the mean square error is merely 0.35%. And in this case study, we introduce or investigate two training instance settings. And the first one, we'll be only using the boundary and initial conditions. And in the second, we also include interior training inputs as well. So two optimizers have been used in this case study. The first one is the limited memory bound BFGS algorithm, and the second one is the Adam optimizer. So let's see the results. So in the first training setting, where we only used initial and boundary inputs and paired that with the LBFGSB optimizer, we do see the PIDL that's trained with the parabolic version of the LWRPDE has a significantly smaller LWR error, or indicating a much more accurate reconstruction result. And we also observed that from the snapshots, or those in these figures. So if we look to the figure on the right, with the hyperbolic version, and we really see that PIDL trained with the hyperbolic PD struggles in reconstructing in the areas with data discontinuity or with shocks. So if we look at the snapshots at t equal to 0 and t equal to 0.5, especially at when x equal to 0.5, that's where the reconstruction is really different from the ground truth, or is in this case, PIDL is not being able to capture the shocks or the patterns in this data set. And we'll observe the similar results with another optimizer with Adam as well. And again, I want to point out to the to the snapshots, and we see where the real difference, or like where the majority of the reconstruction error comes from. That's in these areas where the shock waves are present. So here's the summary of the results in the first training setting. In this case study, we see that the PIDL trained with a parabolic version of this LWRPD has again significantly lower L2 error in reconstruction and achieving much more accurate results. And in the second training setting, we included the interior points and comparing, or like when we look at these 4 subfigures on this slide, and we notice subfigure A, again, that parabolic version PDE with LBFGSB optimizer has the best reconstruction results. Further indicates, or like further strengthens our conclusion that this is what's happening, or like the limitations that we observe with the hyperbolic LWRPDE here is valid, that the parabolic version will have a evident advantage in helping PIDL in understanding this traffic state data. Now we move on to a case study where we use the field data. And again, this field data comes from the next generation simulation. We use the velocity, we use the density on US 101 highway segment in the morning rush hours. So from these data, from this figure, we are able to see the shock waves propagating in these during this morning rush hour time. And here is the reconstruction result. So here, what I first want to mention is this experiment is conducted for the purpose of research. So again, we see the black dots actually marks. We used all the training, all the initial and boundary training instances. And in this case, it's a typical training setting for learning a mathematical PDE, but not really realistic in traffic observations, since we cannot obtain all the traffic state at all the location at or like at any time at x equal to 0 and x equal to 2000. But here, what we observe is actually both the parabolic version of the LWRPD and the hyperbolic version will not have a good reconstruction result, and that further suggests that there is a limitation of PIDL for TIC in this training setting, in this only using initial and boundary condition setting, which is typically for learning mathematical PDEs. So we suggest a few mitigation directions to improve these results here. So the first point or first direction that I want to mention is, as we have seen from the case study using the testbed data, that adding this diffusion term and switching this hyperbolic PDE to its parabolic version will greatly help or improve the reconstruction results, as we have seen that the PIDL trained with parabolic PDE has a significantly lower LWR error in the final reconstruction results. And the second strategy that I want to mention here is after reviewing the relevant literature, we suggest including the observation and collocation points around the shocks will help capture the traffic pattern and improve the PIDL results in TSC. But actually, this strategy also brought out another issue or challenge, that is, how would you identify the shocks in the data that you are trying to learn? And that's also another research topic, but I just want to mention that these mitigation strategy actually comes at a cause or potential setback as well. The third point here we want to mention that comes from the case study that we have seen in the part 2 video of this video series. In the validation of PIDL for TIC, where we use, again, the ngSim data set, but we use 10% and 14% of traffic observations, which are the interior training instances. So the strategy, or like the reasoning behind these incorporating interior training instances, it actually will help the data representation from the training instance of the entire traffic state field. So your data observations will come at a diverse location on this road and at various timestamps, and these representation of the field will help PIDL in terms of learning the traffic state. And finally, we want to suggest this direction of changing the learning architecture of PIDL neural network, as recent research suggests attention-based recurrent neural networks are actually going to be helpful in using this physics-informed architecture for state estimation, or like learning a partial differential equation. So, so here you have 4 mitigation directions that can be adopted or can be considered when you want to think about how we can improve the PIDL performance for TIC. And next, we are going to look at the PIDL implementation with nonlocal physics. So in this part, the reasoning or the scenario that we're considering is actually traffic is in Denver, or there is limitations of local traffic representation. And by that, I mean, we never consider this realistic scenario in real life, that drivers do not react to their local traffic. But instead, you will always perceive the conditions ahead of you. So for instance, when you are driving, you will look at the traffic signal at the next intersection. And if that signal turns red, and you will be decreasing or decelerate your vehicle speed ahead of that intersection. You won't like go just go on like full speed, and once you reach the intersection, and then you immediately stop. So this accelerating and decelerating process is a gradual procedure, and you will actually make your decision ahead of time. So nonlocal physics, or nonlocal traffic states, considers this realistic scenario and actually use this nonlocal traffic density in depicting the traffic relationships, or categorizing the traffic flow conditions. So let's see how that works. So here I'm just going to recall a local version of the LWR equation that we have previously seen in the first 2 parts of the video. And again, like if you're not familiar with the equation here, you can always refer to the previous 2 videos and to see, to get more relevant information there. And here I give the local version of the Green-Shields fundamental diagrams. What I want to say is, in the second row of equation 42, we see the velocity here is related to the local density. So Vxt is related to rho xt here. And again, pairing this LWR PDE with Green-Shields fundamental diagram, we are going to land the equation 43 here. So now let's see what the nonlocal traffic state means here. So nonlocal version of the traffic density will include a perception window here, which is denoted by the parameter W. And we call this nonlocal density rho n. And it is a convoluted traffic density in this perception window. And we see in the second row of equation 44, now my local velocity Vxt is related to the non-local density rho n, says the notation n there. And continuing in pairing the Green-Shields fundamental diagram here, we will have equation 45. And again, in this second row, we see Vxt now is related to rho nxt with non-local density in this case. So now, if we combine the LWR with non-local density in this Green-Shields fundamental diagram, we will have equation 46. And now, in this equation, the partial derivatives of the non-local density rho n and the local density are treated as two separate variables when we compute the partial derivatives, and that's how we can acquire this non-local version of LWR paired with Green-Shields fundamental diagram. So since we talk about non-local traffic density, the kernel function is actually how we can achieve or calculate what this non-local density means. So, so these kernel functions is how we can apply convolution in this perception window. And we propose two types of convolution kernels in this setting. The first one is a constant kernel, and in that case, the non-local density is the average of the local density values in the perception window. And the second kernel that we adopt here is the linearly decreasing kernel, which in that sense, the non-local traffic density is a weighted average of local densities in the perception window. And this linearly decreasing kernel will assign a higher weight to traffic density that's closer to the vehicle, and further away, that density will be assigned with a less weight in this convolution. So here's the approach overview of PIDL with non-local physics. So what I want to point out in this diagram is now we see actually the physics cost, which is the box colored in this pink color. And to calculate JPHY, we actually need two traffic states here. The first one is the traffic state estimation output, which is what we always have in a regular PIDL neural network with local physics. And the second part is we also need to compute the non-local traffic state, and that will also play a role in calculating the compliance with physics or calculating the JPHY here. And here is the optimization algorithms of PIDL with non-local physics. And again, in this scenario, the JPHY, the physics cost, will include or consider the non-local traffic states, says including this non-local version of LWR PDE into the calculation of final cost term. So let's see the field data validation. We use the ngSim data. We use the density field from the I-80 freeway in this afternoon and rush hour. And so here is the reconstruction results. In these three subfigures, we see on the left is the reconstruction with using the local LWR PDE, and in the middle, this is a non-local version with a linearly decreasing kernel, and on the right, this is a non-local LWR paired with a constant convolution kernel. And from the snapshot, what we observe is this smoothing or regularization factor or impact in adopting non-local physics. So in the end, it did improve the reconstruction results. And as we talked about earlier, this perception window, this convolution in this look ahead area is introducing this regularization effect in training this PIDL neural network in learning traffic density in this case. So finally, we are entering the last section of this research presentation. We are going to conclude this research work, and I'm going to suggest two future directions for continued study in this area. As we mentioned earlier, there's a dire need for precise understanding or capturing the traffic conditions in order to efficiently manage traffic flow. So what this research does is it formulates and validates this physics-informed deep learning approach for traffic state estimation with LWR flow conservation law. In the second video of this series, we see the formulation and validation of LWR with green shields and inverse lambda fundamental diagrams, and the formulation of PIDL with cell transmission model. This work, or today's presentation, also exhibits the difficulties of training PIDL with the hyperbolic version of LWR-PDE. And in this setting, we can only acquire a weak solution, and PIDL struggles with the reconstruction in the areas where data discontinuity or shock waves are present. And lastly, this work demonstrates that incorporating the idea of nonlocal physics can improve the estimation performance of PIDL. I want to suggest two future research work directions. The first one is the current PIDL architecture, or like learning algorithm, required retraining for traffic prediction. And this comes from, we understand traffic state estimation is an important and essential task for traffic management, but there's also interest for traffic practitioners and transportation planners in predicting either short-term or long-term traffic conditions. And each time, given the current training architecture, each time new data observations or data instances are acquired, the parameters, the weights, the biases in this neural network requires recalibration and in order to adapt to the new observations. And so the future work, if we can work on just incoming or like generative models of using the incoming traffic data and preserve the most trained parameters and only updated the last few layers of the neural network to produce accurate online estimation or prediction, and that be of great benefit to traffic management. And the second direction or future work is the inverse problem of model identification. And by that, I mean, given the traffic observations, can we select or identify the most suitable model, either that's LWR, either the CTM, either that's green shields fundamental diagram, or maybe some other versions of diagram? Can we identify the suitable model for training from data observations? So this inverse problem is also a very interesting research area that can be explored in the future. And that concludes my research presentation today. And I appreciate your patience with me in watching this series of videos, and drop me a line if you have any questions. And I will continue to post and present my research work. So I look forward to talking with you in the future. Thanks.